Okay, starting our last lecture in this unit, it says, where, oh, where are my electrons? And so we're going to talk, now that we've looked at the electrons, how they interact with light and everything else, we're going to look at how we kind of organize them. The learning goals. Students will understand the Octet Rule as a general rule for electrons, understand the electrons exist in orbitals and sublevels. We'll be familiar with the Aufbau Principle, the Pauli Exclusion Principle, and the Hund's Rule, and relate electron configuration to the periodic table. So, jumping into this, what we already know, electrons can transition between the ground state and the excited state if they absorb energy or emit energy in the form of light. And the absorption and emission involves radiation, so either absorbing that radiation or emitting that radiation. And that electrons tend to move towards the lowest energy state. And so we always want electrons stay at a lower energy state because they're more closer to the nucleus and they're more attracted to the protons. What we learned in the lab, that electrons have a more specific direction than just levels. And so in looking at it, we know that it's not just an energy level, that electrons, the address depends on several different factors. And so what we're trying to do here is we're going to look at the address of the electrons. So the first thing we're going to look at is something that we call the Zeeman Effect. The Zeeman Effect is the emission lines split up into different lines when subjected to a magnetic field. So when we're looking at those bright line spectrums, if we take one of those lines and we put it through just a really big magnet, what we see is it goes from one line breaking up into three small little lines. And what this led to, and what it means, is that not all electrons in the same orbital are equal electrons. And so there must be suborbitals. So these energies, these orbitals, can break up into even smaller pieces when they're broken up into a magnetic field. So the first type of orbital that we'll look at is what we call an s orbital. It has a maximum of 2 electrons, so only 2 electrons can fit in there. It has a spherical shape, so it's round. And orbitals, basically what they are is they are a 90% probability of finding an electron. So basically we're saying that we're pretty sure that an electron is going to be in this area. They are the first 2 columns on the periodic table. So they're group 1 and group 2 on the periodic table. That is the s orbital group. The next orbital that we have, they are p orbitals. It starts at the second energy level, has a maximum of 6 electrons, so the p orbital can hold 6 electrons, 2 each in the 3 orbitals, and so the suborbitals, and so then it has a 90% probability of finding an electron, and it's groups 3 through 18 on the periodic table. And so there's basically 3 spots for them to fit in the suborbitals, and it can hold 6 full electrons. What the octet rule is. Now, the octet rule, we'll get into it very basic here, and then we're going to jump into it later on in the year a lot more in detail. The most atoms that we study in this class have an atomic number that's less than 36. Now, with these atoms on the periodic table, these atoms are most stable when they have 8 valence electrons. And so basically what it means, it's when the s orbital and the p orbital are completely full. And so basically they want 8, and 8 makes them stable, makes them happy, and so 8 electrons will satisfy them. And so that's what the octet rule is. So oct meaning 8. So electrons, or the atoms, like 8 electrons in their outer energy level, 8 valence electrons. Now, the d orbital, it starts at the third energy level, has a maximum of 10 electrons, 2 each in each of the 5 suborbitals. So it has 5 suborbitals. Like with our p, it only had 3 suborbitals. And this is the transition metals on the periodic table. And then lastly, our last orbital that we have is the f orbital. It starts on the 4th energy level, has a maximum of 14 electrons, 2 each in the 7 suborbitals. So the f orbital has 7 suborbitals. And it's a 90% probability to find the electron. And it's the lanthanide and actinide series on the periodic table. So let's look at the periodic table. And would ever wonder why the periodic table has such a crazy shape? Well, when we look at it, our first basically orbital that we have, that's the s. And so we see here, there is the s orbital. Here, the second one we looked at, that is the p orbital. And we look here, this is the d orbital. And down here, that is the f orbital. And the reason why the periodic table has the shape that it has is because of its all the electrons of the atoms and the way that they arrange themselves determines their chemical properties. And so by lining up all the chemical properties, we see that all the suborbitals start to line up, and so it takes on this shape. So basically, the atoms gave the shape to the periodic table. So let's look at our first question. It says, how many electrons can exist in each suborbital? So whenever we're looking at this, the s orbital only has, we can say that it doesn't have any suborbitals, or we can just say that it has one suborbital. And so in the s orbital, it can hold 2 electrons. The p orbital, on the other hand, has 3 suborbitals, and 2 electrons can fit in each one of those, so therefore it has 6. In the d, it has 5 suborbitals, so d can hold 10. And then f has 7 suborbitals, so it can hold 14. So the main thing here that I want you to get from this question, how many electrons can exist in each suborbital? Well, 2. Every suborbital can hold 2 electrons. Moving on to the next one. Which suborbitals are present in the energy levels? So when we're looking at this, looking at the energy levels, the first energy level, which is right here, just holds the s orbital. In the second energy level, we have the s and the p. Okay, and this is a little bit different, but in the third energy level, we're going to have s, p, and these guys here, the different thing about the transition metals is they start at energy level 3. So even though they're on the 4th period, these guys are up in the 3rd energy level. So it's going to have D there as well. And then lastly, on our 4th energy level, what we have, remember that our F block starts at 4th energy level. So not only going to have S, P, and D, but we're also going to throw F in there. Now, what electron configuration is, an electron configuration, it's representing the atom. And basically, it's giving the address of all the electrons. So atoms can be represented by their electron configuration. And how we do this is the number in front represents the energy level. So since there's a 1 there, that's the first energy level. The S, well, that obviously represents the subshell that it's in, the s orbital. And then the number up here in the superscript, it represents the number of electrons. So when we're looking at hydrogen, hydrogen just has 1 electron. It exists in the first energy level and in the orbital s. Fluorine, on the other hand, we see that it has 2 plus 2 is 4 plus 5 is 9. It has 9 electrons, so therefore it exists. 2 of them exist in the 1s orbital, 2 of them exist in the 2s orbital, and 5 of them exist in the 2p orbital. And this is how we represent and show where the electrons are for an atom. So, the first principle that we're going to look at is called the Aufbau Principle. And basically, what this is that electrons fill up the lower energy levels first. So, you can think of it's kind of like filling up a cup of water. When you fill up a cup of water, it doesn't start filling up from the top. Well, electrons are the same way. They start filling up from the very bottom. And so within each suborbitals are filled, they fill in a very specific order. And this is kind of when I took chemistry that we had to learn this, where we had to write it out and draw all the arrows and everything else. But I'm going to show you how to use the periodic table to really help you learn the orbitals and learn the Aufbau principle, which that means just basically how those electrons fill. So it starts with 1s, and then it goes to 2s, and then it goes 2p, 3s, and then it goes 3p, 4s, and then 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 5f, 6d, and so on. And so basically it follows this order. So instead of memorizing it, we're going to use the periodic table to help us learn it. So using the Aufbau principle and using the periodic table, remember what we have. This is our S block. This is our F block. This is our D block. And this is our P block. And remember, this is just the wide version of the periodic table. This is normally how the periodic table is supposed to look, but we just make it a little shorter, and we see it basically with the lanthanides and actinides down here, and that's just to save room on the walls of chemistry classrooms so they don't have these huge periodic tables. So to know the order in which we fill, all you do is you start here at our hydrogen and you just keep going. So the order is 1, because we're on the first energy level, S, and we could say that we have 2 there. And then the next one is 2, S, and we keep going all the way across. The next one's 2P, and all those guys are 2P. And then we have 3S, and then we keep going. And we have 3P, then we have 4S over here, and then remember, this is the only trick to this. Remember that D starts at 3, so this is 3, 4, 5, 6. So this is actually 3D, and then remember, these guys will follow the energy level, so that's 4P, then 5S, keep going, 4D, then we have 5P, keep going, 6S, and then remember our F block starts at 4, so 4 and 5. So we have 4F is right there, and then we have our 5D is right there, then we have our 6P is right there. And remember, for the S and the P's, all we do is we look over here at what energy level we're on, and then for the D's and the F's, just draw it right there. And that gives us our order. So let's go ahead and practice this and actually write the electron configuration for fluorine. So how we do this is we first find where fluorine is. It's right there. And what we're going to do is we're basically just going to count. We're going to count until we get to fluorine. And remember our blocks. This is S, this is F, this is D, this is P. Okay, so we count. This is our first energy level. We're first energy level, so we are 1. It's our S block, so we write S, and then we go count 1, 2. So we write 1s2. Then we keep going because we haven't gotten to fluorine yet. This is what energy level? 2. So we write a 2. And then it's S block, and we count 1, 2. So 2s2. Keep going because we're not to fluorine yet. And then we go, this is, remember, energy level 2, and it's P block, so 1, 2, 3, 4, 5. So 2P5. So our electron configuration is 1s2, 2s2, 2p5. Let's move on to the next one. It says write the electron configuration for nitrogen. So all we do, find nitrogen on the periodic table, right there. We're going to count until we get to nitrogen. Remember our blocks, S, F, D, and P. So we count energy level 1, and this is S block, so 1 and 2. And I know helium's all the way over there, but it's considered in the S block. So 1s2, Then we go to the next one. This is 2 s block 1 2. So 2s2. Keep going. This is energy level 2 p block 1 2 3. Made it to nitrogen. Put a 3. So the electron configuration for nitrogen is 1s2 2s2 2p3. Jump on to the next one. Let's find this one. It's zinc. Now remember, we have to do a little bit of remembering. This is S, this is F, and this is D, and this is P. Now remember, the D block starts with 3. So it's 3, 4, 5, 6. Okay? And when we get the really big ones, remember that our F block starts at 4. It's 4, 5. So we just have to remember that. And that S and P, they stay the same. So there's zinc. We're going to have to do a lot of counting here. So we start, it's energy level 1, 1s2, 1s2. Keep going, 2, S block, 1, 2. So 2s2. Keep going, we're not to zinc yet. And then we have, that's 2p. We're in the p block now. 1, 2, 3, 4, 5, 6. So 2p6. Keep going because we're not to zinc yet. We're energy level 3 now. S block, and we have 2 of them. 3s2. Keep going because we're not to zinc yet. We're in P block now, and it's 3p, and we count 1, 2, 3, 4, 5, 6. So 3p6. Not there yet, almost. So we have 4, and then we have S block 1, 2. So 4s2. And we got to keep going. And finally, remember that this is 3, and this is D block. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the last one would be 3D10. And that would be our electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. And that represents zinc. Now, some other rules that we have for electron configuration and for electrons in general one of them is the Hund rule, and so that's Hund's rule principle, and that electrons exist in pairs, and electrons repel each other, and that one electron in each subshell orbital until it needs to double up. What this represents here is this basically represents electron configuration, and we call these our energy level diagrams. And so what we're doing is we're representing the electrons, and we're representing their spins by giving them arrows, up arrows and down arrows, and we're representing where they are. And so basically what this means, the Hund rule, to really sum it up into an easy definition, is that you always put up arrows in each subshell before you put 2. So like here, this electron could have gone right there and stayed away from that electron. And so electrons don't like each other. They repel each other. And so basically it pushes into another subshell. This is wrong. So you always want to fill, and we'll practice this, fill the arrows in, 1 in each subshell before you put 2 in the other. And then the last one we'll look is the Pauli exclusion principle. And what this is, we're also going to use our energy level diagrams here. And basically what this says, the Pauli exclusion principle, is that no 2 electrons can have the same quantum number, and so it can't have the same address. Really what we need to know is that you can't have 2 up arrows. So see how this one's going up and that one's going up as well. You can't have 2 up arrows in the same little shell, in that same subshell. So let's look at energy level diagrams, and it'll help us learn the Hund rule and the Pauli exclusion principle. Electron orbitals are lined up from top to bottom, and so the orbitals and suborbitals are filled according to the rules. So the orbitals, we have our S. The suborbitals represent the little boxes, and we represent them just by drawing lines. Okay, so let's practice some of these, or actually let's define the Aufbau Principle, Hund rule, and Pauli exclusion principle, because we'll use these when we actually draw some of these. The Aufbau Principle, basically, remember, that's just the filling up. It's the order in which we fill. That's that 1s, 2s, 2p, 3s, 3p. It's following the following the order on the periodic table. The Hund rule, and what I would get from this, the Hund rule, fill each subshell with one arrow before you put two. And then the Pauli exclusion principle means that you can't have two up arrows or two down arrows. They have to be opposite. You always have an up arrow and you always have a down arrow. And that's basically what the arrows represent the spin of the electron. And so which way is the electron spinning? Okay, next one, it says draw the energy level diagram for nitrogen. So we've already written the electron configuration for nitrogen. Remember, it was 1s2, 2s2, and then 2p. We count 1, 2, 3, so 2p3. What we're going to do is draw the energy level diagram. So we draw 1s, and then 2s, and then 2p. Now remember, the s orbital, basically it only has one subshell, so we put one line because it has one subshell. P has three subshells, so we draw three lines. 1, 2, 3. And then all you do is you fill in the arrows that correspond here. So in the 1s, you're going to draw two arrows. One up, one down. In the 2s, you'll put two arrows. One up, one down. And then in the P, you're going to put three arrows. And remember, to follow the Hund's rule, we have to put one in each one of these first. So 1, 2, 3. Okay? If we would have put and mixed it up, say we had done this, and put 2 in that one, it's not right. Okay? And then, since they're both pointing in the same direction, that violates the Pauli exclusion principle. So, to follow them both, all we go is up, up, up. And then if we have more, say we had 4p here, say we were dealing with oxygen, we would just put 1 going down. And so basically up, 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 and then down, down, down. Now, if we look at electron configuration and you're doing it for a really, really, really big atom, it can take a long time. Like when we did it for zinc, going all the way back to zinc, this one took us a very long time, and we had to sit there and count and count and count and count and count, and that takes a while. And so to kind of shorten the process up, what we do is we can write what we call as the noble gas notation. And so it's kind of a shorthand, and so it's a shortcut for electron configuration. So for potassium, instead of writing this whole thing, what we can do is, if you look, the 1s2, 2s2, 2p6, 3s2, 3p6, that's 18 electrons. That's argon. Now, the only thing that you can kind of put in brackets is a noble gas. That's why it's called the noble gas notation, because that's what you can put in brackets, and that's what you can use. So it's just a shorthand, shortcut version. So instead of writing that whole thing out, all we could do is just put argon. That represents the first 18 electrons, and then finish with the last part of the electron configuration, 4s1. So let's go ahead and try this. And it says write the appropriate nuclear symbol notation in the electron structure for a non-ionized atom shown below. And so what we're going to do here is we're going to go ahead and write out our electron configuration and our nuclear symbol notation. So when we're looking at this, what we do is we can go ahead and count up all the protons. So we have 1, 2, 3, 4, 5, 6, 7, 8. 8 protons. So I know that we're dealing with oxygen. And then we can go ahead and count our neutrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 neutrons. So our mass number is going to be 18. And so there is our nuclear symbol notation. And so we want the electron structure, or the electron configuration for oxygen. So when we're doing this, since we have it's non-ionized, so it's going to have the same number of electrons as protons, we have 8. And so we can actually use, well, let's use one of our periodic tables to do this. So we'll just use this periodic table and find the electron configuration for oxygen. So we see we have 1, and then we have S1, 2. So 1s2, and then we have 2s1, 2. And then 2p, 1, 2, 3, 4. So we did that, and what we could have is that we have 1s2, 2s2, 2p4, and that would be our electron configuration. Our next one, it says an atom with 34 protons have an electron structure notation shown below. It says write the proper noble gas notation. And so what we would do for this is when you're looking at it, this has 34 protons. And so what we can do for this is we're going to look at the element that has 34 protons. So when we're looking at it, 34, find it right here. That's selenium. And so what we can do is what's the noble gas that's less than 34? Well, it'd be argon and it'd be 18. It'd be that right there. And so if I wanted to write the shorthand version of this, I could take the first 18 electrons, which is right 1, 2, plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18. So I could take all of this out and just write AR. And then just put the rest of this right down there. And so it'd be argon, and then we'd have 3d10, 4s2, 4p6. And that would be our shorthand version. So just AR in brackets, and then just the rest of this. 3d10, 4s2, 4p6. And that would be our shorthand version for that selenium atom.